So I'm Bill Press. By now maybe you figured that out. And with Allison, I've had the pleasure of being the lead chairs of the steering committee or program committee of this meeting. You may have noticed that yesterday's program was optimistic and upbeat and this was kind of the intent of the program committee, that we should start off with that stuff, but not lose track of the more sober and cautionary aspects of the subject. And so you may have noticed that today is that more sober and cautionary, and this session will largely be of that nature. I hope we haven't overdone it and that people don't load their pockets with stones and walk into the River Thames after this session. And as a partial antidote to that, in this session, we're actually going to start off hearing from Yolanda Gill, who is, I think, more on the optimistic and upbeat side of things. So maybe that will raise our spirits enough that we can then not walk into the River Thames. Anyway, Yolanda Gill is at the USC, where she is the Director for AI and Data Science Initiatives in the Information Sciences Institute of the Viterbi School of Engineering. And her topic is AI scientists as partners in scientific discovery.
Thank you very much. Given this title, you won't be surprised that I asked the question this morning about my excitement to see this concept of an ecosystem in science where we partner with AI scientists. And if that's a possible vision, what would be the role of these AI scientists? How do we get to a place where we trust them as part of the ecosystem, and what kind of role could they play? So I want to talk a little bit about that. One thing is, since this session is about responsible use of AI in science, one thing is that I would like to recognize the shortcomings that we have as humans in doing scientific research. So I have a few select pieces of work. I've been using this slide for 10 years now, so I'm sure there's more recent examples. But at the time, I wanted to point out that humans are not necessarily very systematic. So my example is a study that was done by hand of the fossil record, collecting from many papers a whole compendium of the fossil record, and this was done by hand. And Shannon Peters at Wisconsin tried to replicate that by reading the papers automatically. And my sense is that the automatic natural language extraction would not be as successful as the manual extraction, because the scientists are reading the papers and actually understanding, but actually it extracted a lot more information than the humans did moving through the papers by hand. So that was really a surprise to me. And it tells us that when we do science, we don't always know and we don't always use the information systematically. Another thing that we do as humans is we make errors. There's papers that are retracted. But my favorite example is a genuine error of two economists at Harvard that did an analysis that a student could not reproduce. We heard this morning about students reproducing work. And the student could not reproduce the work and asked for the data and realized that in the spreadsheet there were a few countries that have been omitted from the study, and that kind of changed not the overall recommendations of the study, but really the details of the results. Humans are also biased. So I have an example from an AI system that actually generated hypotheses from data, and the hypotheses that had been published in the literature based on the same data were a subset of what the AI system was suggesting. And when the authors were asked, they said, yeah, one could generate that hypothesis. I just don't particularly think it's interesting. But it means that we tend to kind of bias the way that we look at science. And then finally, poor reporting. We had an earful this morning about reproducibility and how we write papers. And in fact, some of our workflows and our analysis are very complex procedures that are well known in cognitive science to be very hard to describe just with words. But we tend to do very poor reporting of our work. So I pose to you this very simple question of, can we get AI to write papers in the future? And maybe the papers that AI writes are a subset of what we consider papers today. Maybe they just write the analysis of some data. Maybe they venture into generating a hypothesis and showing their results. But what would it take for an AI system to be able to generate papers that are more systematic, that are more, their reporting and the methods are reported accurately? If the AI was able to generate these methods and run these methods, then you could potentially have an easier time comparing methods together, and also updating or building on prior work. I think that also the AI system could explore variations of the methods or uses of the same methods for new types of data in new domains or in new disciplines. So I would like to see AI do this, and to do that, we have to have an AI that has a representation of some of the reasoning that goes into how we select data and why is it appropriate data to the questions that we want to answer, etc. And if AI systems are able to write papers, why not put them to work to reproduce published articles if they have enough knowledge of methods and how we do science? And eventually, just like our students, we may ask them first to reproduce some existing work, and then they get promoted to really being research assistants and being co-authors, and finally they are equals and collaborators. So maybe our AI scientists can follow that same path. If I think about this, and the picture on the left it has a lot of logos of projects that my group has done over the years, looking at different types of scientific knowledge that we use in doing science. But if I think about this, here's the picture. I apologize for the formatting. I don't know what happened there. But if I think about it, there's broadly speaking 6 categories of intelligence that we use in science, and I think the 4 in the middle are the paths more traveled, in my view. So the path of sensors and robots and intelligent sensors and optimization techniques to direct sensing in terms of using AI to reason and observe the world. Another aspect is using AI for optimization and be able to search complex spaces and hone on potential solutions. Modeling, we've heard a lot about, and what I call consolidation, which is to read the literature and summarize or integrate or extract particular pieces of information. So I think that those 4 areas are very widely explored in terms of AI for science. On the very left is an area that I've been very interested in, which is reflection. And it's what we would see as planning and problem solving in terms of what is the goal of a study, what is the hypothesis, what is the question, and how do we reason about that question to find relevant data and methods. Another area that has been less studied is creating new knowledge, so inventing new methods or changing a paradigm, really interesting ideas that have to do with the creativity that we see in science. So I think that those 2 areas are less explored, and they pose a lot of interesting challenges for AI research, and they can really be game changers for science. Because I've been curious about how can we get an AI to write papers in the future, I started an effort very focused on geosciences. We had about 30 early career researchers that lived and breathed the difficulties of reproducing others' research and wanted to do science differently. They were extremely motivated with this. And they spanned all areas of geosciences, from geospace, volcanology, climate, hydrology, all kinds of areas. And thinking about how they would like their peers to write their papers and report their papers so that they could build on better. And they participated in a special issue of a journal of the American Geophysical Union to show these exemplars of what the papers in the future should look like. And it's not just about reproducibility and reproducible science, but we also incorporated principles from open science and from digital scholarship, which means that if your paper is very reproducible, but the data is sitting in your student's local directory, it might not be findable in 5 years when the student graduates. So there's more to this stewardship of science than reproducibility alone. So we created this movement, this initiative. We've been expanding it. These are ideas that have been taken in geophysics, in neuroimaging, but also we've transported them to AI in many ways. Our colleague Odd Erik Gundersen has done a lot of work on analyzing papers in the AI literature in terms of how they follow these principles. So these scientific papers of the future have given us a lot of information about what scientists would like to see in the papers and what would be a proper way to write them so their colleagues read them, but also AI systems could read them more properly and understand the science. So that's my personal preference. So we've worked on a number of projects to capture this kind of knowledge. Let me mention a couple of them. One is called DISC, and it's about automating hypothesis testing and answering questions. And so we've used these ideas in various domains, going from a question to a finding, using a representation of how the scientists solve problems. And so we capture in structures how do they describe the kind of data that they need to answer a question. We typically retrieve data from shared repositories. We look at how maybe there's a lot of different types of relevant data. How do we join them together, etc. So a key idea here, just to leave you with a novel concept, is the idea of a line of inquiry, which tells us, given your question, how do I formulate a query with a lot of details about the type of data that would be relevant to that question, and then how would I analyze the data when it comes back? And very specifically, the question gives us variables that we can bring into the data query, and the results of the data query give us information to set up the analysis and the workflows that we run later. When we do this, then we have a very detailed record of what was done, and we can explain how the data sets were found, why a data set is not there, etc. It gives us also a very interesting new capability, which is that we can run that analysis when new data comes to light. So in neuroscience, neuroimaging in particular, we work with the Enigma Consortium, where there's hundreds of institutions that contribute new data and are collecting data continuously. And so it is their desire to be able to update the results of their published papers continuously. I want to give you really quickly some other examples of this line of work coming from paleoclimate. So if you've seen the IPCC report and the very famous hockey stick diagram, it takes hundreds of scientists working for 3 years to really normalize the data, integrate the data, and create these analysis. So there's an opportunity to do a better job of automating these aspects of their workflow. And so the work that we did was, can we go from the question to automating this process? And one of the places in their workflow where we introduced AI was a form of AI-mediated creation of data vocabulary standards. So you have samples in paleoclimate from drilling in some place, for example, in the ocean, and or maybe drilling ice cores, and each one of those types of samples are described in different ways. They all lead to some hypothesized temperature, but they have an entirely diverse vocabulary because these communities are very different and the type of sample is so different. And so they were able to collaborate online, mediated by this AI system, on what would be common threads in describing this data and what types of vocabulary would be different for each of these types of samples. So very interesting work on a semantic platform, a semantic wiki that was an extension of Semantic Media Wiki that enabled them to add vocabulary, reuse vocabulary, and have a human editorial process to really help normalize the effort. So this was done with no big meetings and a big overhead. This was done as they were describing their data sets. Another place where we insert AI and reasoning is in doing the workflows and the analysis. So at the top of this diagram is a workflow for spectral analysis. And at a high level, it's always the same steps, but depending on the time series that you have at hand, you want to do that step in different ways. And you may omit some steps given the data that you have. And so we have ways to reason about the characteristics of the time series and the data and the specific algorithms for each of the steps to create instances. So when you have thousands of time series data points, you really want to have this ability to intelligently customize the data analysis. So we've been able to automate this process, and we're very excited about it. And it's a flagship example of how AI can help streamline science workflows. So back to the original point of could AI write the scientific papers of the future, I do believe that there's a lot of interesting cognitive frameworks to represent how scientists solve problems, how we go from questions or hypotheses to findings, a lot more work that needs to be done in this area, and really thinking about the trajectory of having these AI assistants helping us fill up pieces in science. I think that when AI becomes a collaborator, we have to make it really a partner. And there's a long list of desiderata of not having AI systems that are passive, that we have to task constantly, that we have to check their results constantly. So there's a lot of room also for AI challenges here. And my conclusions is that we have to really think about how AI scientists can reflect on the problem-solving steps that scientists do pursue that will help us make them more independent and contribute to the AI ecosystem.
Thank you very much. I now have the pleasure of introducing Stu Feldman. Stu is President and Chief Scientist of Schmidt Sciences, only the latest in a career with many high-profile positions in supercomputing and in the advancement of computation generally. And I think to some extent you're going to lead us into darker territory, but no, he's neutral. So we're doing the neutral transition into darker territory. Stu is going to tell us about science challenges of AI, openness, scientific norms, speed.
a pleasure to follow Professor Gill. If I might make one tiny comment on your first example, your statement was not completely accurate. Yes, the famous Harvard paper, as you said, I assume that was Rogoff and Reinhardt, which had the small error of not selecting 5 of the 20 countries it was analyzing in an Excel spreadsheet. The net result was to get the sign of the effect wrong, and this paper was heavily quoted in support of austerity cuts in 4 countries. It's a pretty high return on a stupidity investment, and didn't need AI to do it. Did need a certain amount of fumble fingering, however. So yes, it was actually an important failure, not just a failure. However, I do look forward to the AI scientists. I will mention I have the pleasure of leading Schmidt Sciences, which follows up on many of the research activities we'd had in Schmidt Futures. And one of those, we've currently funded approximately 200 postdocs in learning how to use AI to support non-computer science research, in addition to lots of other projects that some of you probably know about. So basically, this is not the doom and gloom talk. This is the let's get serious talk, as it were. I strongly am excited by all the wonderful things we are doing with AI. The neural nets followed by the LLMs have just radically shifted whole fields of science and computing. I basically won't talk to anybody who does computer vision who doesn't use AI somewhere. It's just not a useful conversation, for example. However, the radical changes where you get all the clouds of, oh, woe is me, are really analytic continuations of where we were before. In most cases, it spotlights failure modes we had and then helps exacerbate them. But we need to think about why we were, as a science field and perhaps society, getting things wrong before. Bad data, lack of diversity and bias in it are not, unfortunately, new. Data analysis that is itself incorrect, thank you, Rogoff, and more seriously in medicine and such, is rife and has been for years. What's new here is the scale of the data and the opacity with which we treat it. However, many of those issues were there. Some of the issues involving medical research were highlighted earlier and today, and among other things, the data available are radically non-diverse since they mostly come from either organized health systems or rich countries, and therefore you have a bias where they come from. The publisher pressure, publish and perish pressure is continuously getting tighter in many fields. At lunch, the previous conversation, we were talking about the very fast turnaround in writing papers in AI in many cases, where many of them might not have been impressive in other contexts, but in a very rapidly changing field, progress happens suddenly and often. Reproducibility, well, we've already been discovering lots of old bad papers in the past. AI wasn't guilty of many of the most famous reproducibility failures. However, it does help automate fraud and other failures. So we're going to see a lot more. And there's going to be the cat and mouse game of AI looking to catch the last generation of scientific misconduct while the people get smarter about evading the tests. But really, this is a endemic problem in our culture, not just AI. Depending on black boxes, that's a real interesting one here. even if somebody opens the box and congratulations, there's a trillion random parameters in it, Merry Christmas. What are you going to deduce if you actually have the easy white box, unless you also happen to have the 10,000 GPUs you need to play with it? This is a very real problem, but we already were using tools that we couldn't play with. The telescope you're using, they don't appreciate it if you try taking it apart when you go to the mountain. It's a black box or semi-white. And much of the software we use is commercial and not available. So what's different here is the magnitude of the black boxes, and that's important. The fact that the field is at the moment heavily concentrated and dominated by, pick a number, between 3 and 6 commercial entities. There's a standard truism, at least in American antitrust, that the average industry is dominated by 3 companies, and that's the stable number. You can check this for going back to 75 years. So it's not a shock. It's just annoying when they're in your way instead of bothering your butcher who can only buy meat from 2 companies, 3 in the U.S. Another real problem is science just isn't a big enough market to affect what the tech companies are really going to do. The chips are being designed, for games, followed by ChatGPT, not for what the climate modelers here would like, which is probably more than 4 bits of precision. 64 was viewed as low for some simulations, and moving on 8 is really a problem. Okay, but we've lived with this problem for a long time. So I'd just like to point out we're in a state of continuity in practice. However, quantity does change quality in reality. And so the fact that natural language and gesture input for the masses is here changes both society and the way we think about how you deal with computing. When prompt engineering, a field that did not exist 3 years ago, is now perhaps the most important branch of software engineering, it's a real change. Having easy use, not just access, but asking Google to look for you, but actual use of 10% or more of all of human knowledge is a real change. And I emphasize the word use. The closed research loop, which when automated with AI, allows serious scale to be done in a laboratory. And if you do multiple loops, there is the small question of who did the research when a computer made the decision about what to do and then ran the automation line. But I'll get to that. The fact that we have not just weirdly imperfect equipment, but intentionally random seeded inputs into LLMs and such, which mean you're guaranteed not to get the same answer the next time you ask. And that's a little shocking in a world where we were taught about reproducible science and that electrons only have 1 mass. Well, give or take how much of it wants to tell you this time. And that's really a change. And it's really hard to match a period of blazing change in technology to the scholarly timescale, the thinking timescale. Computers may not think as deep as you do, but they think a lot faster. And they're probably getting better faster than your brain is improving at a fraction of number of neurons per day. And the trust and safety concerns are quite real. I won't spend much time on that, but I'm happy to spend as much as anybody wants. So scientific norms are radically at risk, however, and the question is, how do they change things? And let me be clear. When you think seriously about this, scientific norms are partly those of a medieval guild, restricting entry into the field, self-governance of the field, formal acceptance of that professional entry is subject to societal public good, and tell that to your cosmetician, who is as more of a professional than you are, since you don't actually. Well, you probably don't belong literally to a guild. Or a professional certified field. In the U.S., people who cut nails do. Then there are technical norms, and then there are structural norms. To get, pompous about this, I'm not going to quote the Bacons. I'm going to quote Robert Merton, who father of the field of sociology of science, basically. And the principal goal of science is the extension of certified knowledge. He identified several technical norms and a bunch of 4 moral norms, as he called them, for how science operates as a social entity. Technical norms include believing only in empirical evidence. We're standing in the home of that theory. Trust only evidence, and logical consistency, not random assertion. But the moral areas are universalism, which says judging by impersonal criteria, not who said it, but why it's true. Communalism, actually it was originally called communism, but the name became a little unpopular after 1942, and it was changed. Sorry. But knowledge produced by the community must be shared. And it's a weird economy. You get paid in this field by giving away your results and becoming esteemed and famous. It's a very strange economy, but one of the great merits of science. And it's always in tension, and always has been in tension with commercial rights, going back to the Bacons. Disinterestedness, which is curbing of personal bias, and the reward system supports it. Does AI participate in that? And then organized skepticism, suspending judgment until the evidence is good enough. Well, refereeing other institutions are the support for this thing. We heard today about how hard peer review is being made. And how do you verify work that's done by this opaque, intentionally non-reproducible co-worker? So I put those up, and then for interesting comparison, a very nice editorial published last month in PNAS entitled Protecting Scientific Integrity in an Age of Generative AI. It had about 24 authors. I'm sorry if I missed any, but other than Tom Mitchell, William Press, and Jeanette Wing, who are in the room. But a nice piece, and these are the specific recommendations: transparent disclosure and attribution, verification of AI-generated content. People are responsible for accuracy, not to blame the computer or Excel. Documentation of AI-generated data, marking the synthetic data and the intentionally fake images and such. Exactly whether you mark the AI-written text was not clear. Focus on ethics and equity, scientifically sound, socially beneficial results with a desire to mitigate and provide good tools, and continuous monitoring, oversight, public engagement. You will note that these overlap admirably with the Mertonian list. Number 1 is basically the communalism goal, etc. So there's utter consistency here. AI only makes these things more plangent. It doesn't make them new, but it makes them probably much more pressing, because we can make. One of the great advantages of high-speed computing, was an old motto I was told by friends, is you can make mistakes so much faster. And AI allows us to square that. We get the data wrong and the compute. So what are some of the changes? Let me just suggest that you look at the author list of a big paper in Nature, and then decrypt the 15 weird symbols. And when you do, basically one of them says, made coffee for the previous authors. And some of the real ones included provided funding for the project. That's on the author list, not on the acknowledgments. So who had the idea of the problem, who did the literature research, who did the lab work, who did the computing and software, who did the statistical analysis, and again, who did supervision, who provided the resources, who wrote the thing, who got trained. Each one of these has footnotes and so forth. And this isn't in one of the 1,000-person papers coming out of LIGO or CERN, 4,000 for CERN. The major CERN paper was 90% author list. I'm sure they were good to stay. LIGO, the Abbott et al. Paper was actually, I think, equally balanced between amount of text and amount of author. But both of the results, by the way, are the most important things done in this century, so it's okay. However, this is actually what we've got today. And now, which of these roles does AI in practice take over? And then do you credit AI for having rewritten the text so that it's literate? The statistical analysis is unlikely to have been done by you with a quill pen and a piece of paper, even before. The literature research is very likely to be done better by ChatGPT to get you the landscape first draft. So as these things happen, how do we accommodate this inside the world of science? So what's interesting is that we already have this, except for the making coffee part, not a joke. I'm an author of a political science paper that came out end of last year. And for a while, I was first author, because actually I came up with the idea for what should be done. But luckily, another professor and his grad students did all the work. Eventually, I was politely asked would I consider moving to off of the first position because the grad students really needed the credit. Okay, I didn't need tenure credit, but so, okay. Yep, fine. So openness is something we all love to have. We all love talking about it. It's a public good. If research is funded by tax dollars, it ought to be publicly available, et cetera. And by the way, Schmidt Sciences expects our research grants to produce open everything. However, there are real concerns about safety. The usual examples. Do you want your LLM to tell somebody exactly how to put together a nuke, or how to revive smallpox from the published sequences? Maybe you don't. But what are you going to do about it? And now, even better, now that we've got lab automation, would you like the lab robots to put the plutonium together? Ignoring the question of where you buy it. But okay, this is a very hard problem when you generalize it from just Yersinia pestis or U-235. And when you look at the most exciting things that AI is probably going to be doing, look at the harms that social networks have done to the fabric of society through second and third order interactions, not just first order. These are topics that are really interesting research projects. We're about to fund a bunch of them because there's very hard questions buried here. But these things argue against complete openness. Okay, fine.
Do you have conclusions?
Yes. Yeah. I will just slide to show one thing. So they're basically, where we are here is looking at the risk, but the opportunity of scale. We already know, you've heard all of this, but what's really important, I believe, is that we've been riding an exponential. Remember, an exponential doesn't have a knee. It always looks like it's rising up in front of you, and here we are. And the graphs all look the same, basically. And speed, similarly. And I will just, for simple questions, what does this work look like when you have a 3-year grant cycle, a 4-year PhD cycle, a 6 or 8-year tenure or secure employment cycle? And then to leave the proper gloom for the rest of the speakers, I don't think we're about coming to AI winter, but one of the wonderful things about academia is that, boy, can it produce when it wants to. Very few large organisms will double or triple their population in a year, but PhD production can be really effective. And so we will, as always, overproduce. So when will we hit the AI wall? And I would guess under 5 years. But sufficient unto the day is the problem thereof.
Thank you. Okay, that's what neutral sounds like. The next speaker is David Leslie. He's the Director of Ethics and Responsible Innovation Research at the Alan Turing Institute, and he's also a professor of Ethics, Technology, and Society at QMU in London. His topic is the New Tech Bubble, Deflating AGI Myths and Legends.
So apropos of Bill's warning before, in the Royal Society's deep sense of humor, they've invited the philosophical Grim Reaper to the event. It won't be strictly doom and gloom. It won't be let's get serious. It'll be more let's get real. Okay, so I wanted to basically provoke you today. So what I'm going to present is a provocation, philosophical provocation. Can't do much in 15 minutes, but I want to zoom out first and start our reflection on what I call the new tech bubble with a kind of thought experiment. So 3/4 of a century ago, the American philosopher of science, Norwood Russell Hanson, posed the somewhat strange but intriguing question of whether the sun rose for Johannes Kepler. The point of Hanson's provocation was to reveal how the heliocentric world that Kepler moved around in was elementally different from the Earth-centered world of his scientific predecessors. In the world of Aristotle and Ptolemy, the sun rises and the Earth is fixed. In the world of Kepler, Copernicus, and Galileo, the horizon drops and the Earth moves. The sun doesn't rise. These are fundamentally different worlds for Hanson, each being interpreter-dependent and theory-laden. Now, ultimately for Hanson, the worlds that we live in, the worlds that we navigate, are worlds that we together create through collaborative practices of theorization, interpretation, and argument. They are thus worlds that, through the power of collective world-making and scientific discovery, can fundamentally and perhaps paradigmatically change. So this idea that moving from Ptolemy's world to moving to Kepler's world, something is created, something's new, a world image shifts. That's the idea. Now, with this in mind, have a close look at the image on the screen. This is the frontispiece of Galileo's dialogue concerning the two chief world systems, his attempt to promote the heliocentric theory of the universe. Now, what is so interesting about the image is that the universe and its celestial bodies largely don't even appear. Rather, it portrays scientists engaging in conversations, giving and asking for reasons. This is an image of scientific world-making, the birth of modern science as the birth of a tradition of collaborative practices of theorization, interpretation, and argument. And I've taught social theory for a number of years, or history of social philosophy, and I always ask my students I won't show them this, but I'll ask them, what do they think the Galileo frontispiece is? And they all describe, it's got to be the universe, it's got to be, the celestial bodies, but no, it's this picture of communication. So in other words, this is the genesis of the scientific method in action, the genesis of practices of scientific research that bear the originary burdens of reciprocal responsibility, integrity, mutual respect, and rigor. More than just picturing the scientific revolution of heavenly bodies, the image represents a normative revolution of the moral universe, both within and between people. So Hanson's question of whether the sun rose for Johannes Kepler gains new significance in the rising era of large language models and generative AI. Amidst the growing swells of magical thinking among scientists about the takeoff of so-called artificial general intelligence, or the emergence of autonomous Nobel Prize-winning AI scientists, researchers need to take a conceptually sound, circumspect, and sober approach to understanding the limitations of these technologies. They need to engage the affordances provided by such tools with the same kinds of epistemic humility, deflationary skepticism, and disciplined adherence to the scientific method that have functioned as preconditions of the modern scientific revolution, the modern scientific advancement, since the dawn of the 17th century Galilean, Baconian, and Newtonian revolutions. In the short time I have here today, I thus want to sense check our expectations of what role AI systems like this can actually play in processes of scientific exploration, understanding, and discovery by asking and then answering the question, does the sun rise for ChatGPT? Such a question, I'll claim, points us towards the acknowledgement of a fundamental limitation intrinsic to these systems, simultaneously as it prods us to recognize that contexts of scientific discovery are and have always been principal sites for the expression of democratic agency, creativity, and human empowerment. So to motivate this argument, I want to point to an existential threat that's occurring right now to the integrity of contemporary science, a threat that has arisen from the increasing capture and co-optation of scientific communication by a kind of new tech bubble. Now, unlike the Y2K.com tech bubble, the new tech bubble is not a matter of manic economic over-evaluation. Rather, it is a matter of a reckless sort of conceptual hyperinflation. This is a dynamic whereby, in some cases, tendencies to AI boosterism and big tech puffery lead to the epistemically questionable commingling of the actual and theoretical and empirical fruits of data science and AI research. So a commingling of this with dubious anthropomorphic idioms like computers becoming smarter than humans, or with highly speculative claims about so-called artificial superintelligence, a tendency which has often enabled academic, corporate, and entrepreneurial AI rainmakers alike misleadingly to parade contentious, philosophically unjustified, and highly conjectural metaphysical assertions about agency, general intelligence, intuition, imagination, understanding, experience, and similar terms as being the results of rigorous scientific method and technological innovation. Likewise, the aggressive use of ambiguous, poorly articulated, and highly contestable terms like artificial general intelligence has become normalized as a clarion call to founder mythology, research hype, and big tech expansionism as these headlines, you can see them, display well. Now, such a conceptual inflation has not, of course, gone unchallenged. Lauren Goodlad, Professor Goodlad, for example, critically analyzes the term artificial general intelligence as a rhetorical device and a marketing tactic. She writes, quote, "More than a decade into this deep learning paradigm's romance with massive scale, the world's largest tech companies are using the rhetoric of artificial intelligence and even artificial general intelligence to market disembodied, virtual, and effectless statistical models trained on vast data sets to a public accustomed to associating such terms with fictional androids. Anthropomorphic analogies misrepresent the functionalities of data-driven machine systems when they conflate predictive analytics with human decision-making and equate massive data sets with human knowledge, social experience, and cultural commitments." So Goodlad's deflationary point returns us, I want to claim, to the fundamental limitation intrinsic to AI systems that I mentioned before, and thus to this question that I want to ask about whether the sun actually rises for ChatGPT. So to take a first pass at answering this question, it might rightly be said that the sun doesn't rise for ChatGPT or any other generative AI systems because such models don't even in a charitable sense have access to the meaning of the word sun or horizon or world, or for that matter, a rudimentary capacity for sense-making, for theorization, for interpretation, or for truth. Despite their outbursts of rhetorical prowess, generative models like ChatGPT lack warm-blooded access to the world of shared experience, in which the socially embodied pursuit of scientific discovery takes place. Contexts of discovery are human contexts. They are contexts of scientific sense-making that involve the real-life processes of communication that are carried out cooperatively by members of an unbounded human community of inquiry and interpretation. Regardless of how generative AI tools piece together the vectorized representations of the categories and variables around which these data are scientifically organized and grasped, these are humanly constructed and defined through common criteria, established in specific research contexts, and shaped by the interests, motivations, and beliefs of those who collect and manage them. Such categories and variables gain meaning in scientific practice only insofar as they are inferentially interrelated to a meshwork of other categories and variables in an evolving space of scientific reasons and justifications. For the connections of the concepts to be meaningful at all, they must fit holistically into a wider fabric of scientific theories and understandings, a forever developing picture of the world that is the ongoing interpretive accomplishment of an intergenerational community of scientific interlocutors. Now, acknowledging this primitivity of collaborative world-making in the development of scientific understanding should serve a crucial bubble-bursting function in the current rarefied climate of messianic hype surrounding foundation models and generative AI systems like ChatGPT or Claude or other. These systems neither navigate an evolving space of reasons and justifications within a boundless scientific communication community, nor do they partake in the trials and triumphs of experiential sense-making. Rather, foundation models and large language models generate predictions of the statistically likely continuations of word sequences based on the brute force iteration or iterative training on massive data corpora. As sequence predictors, these models draw on the underlying statistical distribution of previously generated text to stitch together vectorized symbol strings based on the probabilities of their co-occurrence. They therefore lack the communicatively embodied and relational attributes and functionings that are actual prerequisites of scientific meaning-making in the barest sense. These systems do not inhabit a lived reality wherein speaking and interacting members of the human community together build and reproduce a common world of shared experience. Gotcha. Using the agency of language to convey intention, to establish truth, and to cope with the myriad problems of existence. In this way, they lack the basic capacities for intersubjectivity, for semantics in the social sense, and for ontology that are preconditions of the sort of collaborative world-making which allows scientists to theorize, understand, innovate, and discover. And so it's precisely for this reason for reason of these limitations that the notion of AGI or Nobel-winning AI scientists, these are matters of science fiction, myth, and legend, rather than measured scientific aspiration. So this leads us then to ask what the proper place of advanced or so-called frontier AI systems is in contemporary scientific research. So let me suggest that it leads us to embrace a more sober tool-based understanding of these technologies as computational instruments embedded in warm-blooded interactive processes. These can serve several salutary functions, and I've listed a few up there. Now, I want to close here then by really just pointing to the need for us to return to the tradition of epistemic humility, collaborative exploration, scientific rigor, and integrity that the Royal Society has instantiated for 364 years. It is a heritage that militates against the kinds of conceptual hyperinflation that can in fact obscure, diminish, or even deprioritize the significant scientific advances that are currently being made in AI for the public benefit. So on the left, you'll see the cover of the Royal Society's recent report on science in the age of AI. Significantly, across its 108 pages, the term artificial general intelligence appears only once, and only to signal that the topic will be set aside for the purposes of the report. Instead, as you can see from the graphic on the right, the paper underscores the tool-based role that AI systems can play in research and discovery to help scientists as computational microscopes and resources that spur inspiration and understanding. The remarkable emergent multifunctionality of foundation models and their capacity to pick up and reproduce patterns of human reasoning through the scaling of data and compute is of a piece with the equally remarkable capacity of deep neural architectures to approximate any computable function with sufficient quantities of data and compute. 2 seconds. Used as a tool to support research and scientific ingenuity, generative AI systems could in fact accelerate theory production and innovation across the sciences, opening almost limitless spaces for scientific exploration by revealing hidden patterns in the otherwise impenetrable heterogeneity of the natural world. From this perspective, scientists could work together to deploy these kinds of algorithmic tools as computational vehicles of observation, assay, and analysis to heuristically probe unbounded search spaces and patterns in high-dimensional biophysical data that would otherwise be inaccessible to human-scale examination, experimentation, and inference. Thank you.
Thank you. And I've consulted our robot masters, and they're happy to have Professor Leslie hiding their true intentions with a talk like the one you've just heard. No, food for thought, and I hope that in the question period people raise questions there. Next talk is Professor Shannon Valor. Professor Valor is the Baillie Gifford Chair in the Ethics of Data and Artificial Intelligence at the Edinburgh Futures Institute, EFI, at the University of Edinburgh, where she is also appointed in philosophy. And her talk is on ethics, integrity, and public trust in AI-enabled science.
Okay, so I was trying to think about by this point over these 2 days, what would not have been said about these things already? I'm grateful that what I expected might already have been covered has been amply discussed today. So I'm trying to bring the focus around to some of the structural and systemic issues that we really have to address if we want to implement any of the really valuable guidance that has already been generated about how to use AI in science responsibly. And I was really glad that Stuart's presentation already highlighted that we're not dealing with a situation in which we have many unprecedented challenges, but what we're dealing with is a system that's of institutions and incentives that's already stressed, that already had weaknesses, and that the introduction of AI is exacerbating and amplifying. And so to perhaps overcome the worry that William put forward that the philosophers would leave us in a place of doom, I want the presentation to focus on the opportunity that we have to undertake some of the structural reforms that have long been delayed within the sciences, that AI might be the final push to force us to make some of those changes. So I'm going to talk about, very quickly if I can, the emerging challenges for research ethics that we see from AI, the challenges for research integrity, the ethical pressures from Gen AI in particular, the backdrop of the fragility of our existing oversight mechanisms and the public trust crisis that complicates things further, and then some concluding thoughts about what needs to happen. So one of the things we perhaps haven't talked about enough is that AI shifts the focus of research ethics, and I've seen this in practice, from individual interests, so particular study participants who might be endangered by a particular protocol, for example, to the vulnerabilities and interests of groups and collectives who may be anonymous, who may be quite remote from the study itself, contained or implicated by the data set, but not part of our research. And so we don't actually have many great protocols for addressing those kinds of concerns. We've also got the fact that AI demands wider areas of ethics expertise than traditional scientific research ethics does. Considerations that are much broader than we're often used to of unfair social bias and injustice, issues around socio-technical safety, dual use potential. Again, none of these are new. We can find examples where these were concerns of research ethics committees and researchers previously, but AI has made these sort of bog standard concerns rather than slightly more exotic ones, and I've found a lot of research ethics committees are struggling to handle them. We've talked about replicability and transparency, but again, these also are issues that can't be addressed entirely at the level of individual researcher integrity and study protocols. Some of the fixes for these things have to be more systemic and institutional. The other thing we need to talk about is the fact that AI is creating some new perverse research incentives, data hoarding, the use of inappropriate tools, the idea that if we throw AI at anything, it's somehow going to make it better, or at least it's going to get more attention. And that is something that we have to address as well. We've had some discussion, and I was really grateful to hear this, of the problem of the power differentials in research that are shifting rapidly toward industry as a result of AI. And one of the things that I was thinking about when we were talking about this earlier is that this is also affecting the kinds of norms of scientific integrity that we take for granted often. So many of you may be familiar of some of the spectacular failures of tools like ChatGPT that have been illustrated by researchers probing for its weaknesses. One of the classic examples is if you take a very complex logic puzzle, like the man and the fox and the sheep and the cabbage and he's got to get them across the river, right, in the boat without one thing eating the other, so it requires many trips, and it's a very complicated but very familiar and often discussed kind of logic puzzle. Well, researchers showed back in April that GPT-4, Gemini, all the leading tools that they tested failed to solve a much simpler version of the puzzle, which is you have a man and a fox and a boat. The man needs to get the fox across the river. What does he do? It's one step. A child could solve it. Put the fox in the boat, go, done, right? All of them gave a far more complicated answer that often involved the boat transporting itself across the river, the man walking back across the river, all kinds of things that tell you that A, this thing can't actually reason at all, because it can't perform the simpler reasoning task that is the composite of the full solution, and that it doesn't understand the meaning of the words, as David mentioned, right? It doesn't understand what a boat is if it thinks that the boat can transport itself from one side of the river without actually being piloted. What I want to focus on, though, is not those limitations, but what happens when those are exposed. Immediately, the AI companies that are responsible for adapting and fine-tuning those models will fine-tune the model and fix that particular weakness, right? If you go online 2 days after something like that gets published, you won't be able to find the fail, make it fail in that way unless you try a different approach. I want to compare that with the norms of research excellence that we take for granted in science, the kind of humility that has been mentioned several times, right? How do we respond to a scientific researcher who covers up a failure of their methodology or their results in this way and make sure that we can't see it without addressing the deeper flaw that it exposes, right? And yet we take these, no one calls out the AI companies for fixing these failures, right? Or not owning them. So I think we have to think about how the erosion of these norms that we take for granted can be affected by these power differentials. We know that standards of rigor in machine learning-driven science are not yet well enforced. Many of you may be familiar with this research, but if you haven't, I would strongly recommend the research of Arvind Narayanan and his PhD student Kapoor, who have talked a lot about how much data leakage, for example, you see in machine learning research-driven publications. Here, data leakage doesn't mean what it means in another context where it's a privacy worry about things that have been sensitive info that's been put into a prompt leaking out of the model later. This is about failure to separate training and test data sets properly in a way that data from one doesn't get picked up by the other, right? So we know that there's a lot of work to be done to get this right. We've got ethical pressures from generative AI that we've already talked about, so I'm not going to elaborate on them. Problems with data provenance, data quality, ground truth contamination, problems with confabulation, which we prefer, ethicists prefer that to hallucination, which psychologizes the model or anthropomorphizes it, right? Now we know that the models will get somewhat better at this, but there is some indication that it's not a fixable problem, that we can mitigate it, but we can't make it go away. And I think that's a concern because rare and subtle confabulations, which will remain, can be more hazardous, I think, to research than obvious ones that any peer reviewer can see. There's a lot of worry I hear from researchers that generative AI hype may be diluting the appeal of more reliable and sustainable machine learning approaches, working with smaller, more targeted data sets, working with models that work perfectly well without having to chew up the kind of compute or create the kinds of confabulation risks that generative AI does. Okay, I want to talk about the existing oversight mechanisms. The word mechanisms has disappeared from the slide, sorry about that. But the peer review system, we've already talked about that. It's been buckling due to higher academic workloads and research volume, and that was before AI showed up, right? I mentioned the way that research ethics needs to catch up with the issues that AI introduces, but research ethics committees and training providers are currently in many institutions not resourced or empowered to rebuild the research ethics frame for AI and machine learning. They know they need to do it, but no one has the time or the resource. A lot of researchers, frankly, lack adequate supervision around these new issues and methods, so they may be working with overburdened, overtaxed senior academics who really aren't investing the time to create this new kind of training that their researchers need to handle these things. That comes against the backdrop, this is where the doom comes in, of a crisis that's already here in terms of public trust and scientific expertise, right? That's already been damaged by disinformation, conspiracy theories, politicians. Public trust in AI is rapidly declining due to the perception of an economic threat and unregulated dangers. I've seen the tone of public discussion of AI on social media and other things shift rapidly just in the last 6 months. And given what good AI can do for science, we should be really worried about that, right? We've also got pre-existing problems of trust in institutions that's been weakened by funding cuts, by politicization, by administrative failures that have been routine for decades. So, what do we do about these things? Well, we can modernize and systematically overhaul research ethics and integrity infrastructure and the peer review resource model. This is long overdue. Maybe we take the pressures of generative AI as something to force our hand, right? How can we rebuild these systems to make them robust again? They're never going to be perfect, they never were, but very few people think they're working good enough, even close to good enough right now. And AI is pushing them to the breaking point. So how do we shore up these systems to make them robust? We need to develop new required methods courses that teach appropriate techniques and standards for rigorous ethical science with AI and machine learning. This just has to be part of the basic research education curriculum. And I don't think we can expect, as I mentioned, overburdened researchers to take this on themselves with each of their PhD students or postdocs or whatever. It's just not going to happen. So it has to be part of the curriculum. A huge thing I think we need to talk about, we absolutely have to figure out how we're going to modify the institutional and disciplinary publication incentives for research success and promotion to reward quality over quantity. None of the guidance that we've talked about here, which is incredible, like the PCAST stuff, all the things that NIST has produced, all the things that Turing Institute has produced, all the stuff that many of the people in this room have embraced, can't be implemented if people don't have the incentives to implement it. If people are still rewarded for business as usual, then only the most inherently responsibly motivated actors will do it, and only for a short time, because they'll start getting penalized for taking the extra time to slow down and do it right. I've seen this in corporations, where I learned very quickly working with corporations that the problem is not unethical people, the problem is bad incentives. And we have to recognize that those incentives need to change. The guidance and principles we have learned so much about responsible AI in the last 10 years. And we don't need more of that, so much as we need a change in the systems and incentives that are needed to motivate people to use that knowledge. And that means creating and tracking new metrics for units and organizations that factor in things like sustainability, things like ethics, and things like rigor alongside our traditional metrics for impact. We can also work with public sector funders and policymakers to buttress research integrity against commercial pressures, and communicate with wider publics about the urgency and importance of using AI and machine learning responsibly in science. How long do I have now?
2 minutes.
Awesome, because that was my last slide, but I did have one thing I wanted to have time for. As a more radical suggestion here, Lewis Mumford, who is a philosopher of technology who wrote about a century ago, wrote something that I started thinking about a lot when I was writing my book recently, and it mentions the Royal Society, so I thought I would mention it here. I talked about how many of the challenges that we're facing require addressing ethics from more than just a technical perspective, more than just what we think of as a traditionally scientific perspective, but require considerations of social justice, equity, responsibility that traditionally fall within the domain of the humanities, or in some cases even the arts. So I'm just going to read something that Lewis Mumford said as a provocation. This is from 1922, The Story of Utopias. Unfortunately, the men who gathered together to form the Royal Society were specialists in physical science, and in the lapse of the humanist tradition through the religious acerbities of the time, they had lost some of their desire for a complete life. As a result, the original charter of the society confined its work to the physical sciences. Insignificant as it now appears in the annals of science, this decision seems to me to mark a definite turning point in human thought. Henceforth, the scientist was to be one sort of person, and the artist another. Henceforth, the eidolon of science and the eidolon of art were not to be cemented together in a single personality. Henceforth, in fact, the dehumanization of art and science begins. It is interesting to note that with the divorce of the humanities from science, art and science entered upon separate careers which for all their diversities are curiously similar. Both art and science, for example, ceased to be the common property of the community, and each of them split up into a multiplying host of specialisms. In this process, art and science made many notable advances, so that this period is usually spoken of as a period of enlightenment or progress. But, and I cut off the quote there because he goes on to talk about the losses to the community of knowledge that come from this split, despite all that we gained from it. And I do think, as a provocation, one other thing AI might do is push us to think about whether that split can be sustained or should be sustained, or whether we might think about the reintegration of the scientific and human personality as a way forward. Thank you.
Thank you very much. How to introduce Martin Rees? I could simply point to the picture on the wall. Martin is former president of the Royal Society. I've known Martin, I know this makes me seem old, not him, but for about 50 years. I knew him in his first career as the preeminent theoretical astrophysicist in the world, and he was a great mentor to me. I knew him then as an iconoclastic, anti-establishment kind of personality. Here he is as the Astronomer Royal and a member of the House of Lords. And he's here to tell us about AI's scope and limits in astronomy and fundamental physics. Martin?
Right, well, Thank you, Bill, and here you have the 3D animated version of the picture there. But let us start by fully endorsing what the last speaker said. We really need to make academia less sclerotic, have new ways of appreciating work and encouraging breadth. So it was wonderful to hear those early talks. And I can't live up to that because I'm only on the programme really due to pressure from Bill that I should say something. Well, I'm an astronomer and space scientist, and I want to say some things about the special perspective which those topics offer in the context of AI. Of course, astronomers, like everyone else, can analyze and draw inferences from huge volumes of data, though the application is not as distinctive from other subjects. But of course, astronomers have been especially excited. And the reason for that is that in the old days, we had far too little data to do much at all. And it's become exhilarating to feel that we've now, owing to technical developments in observing, got almost too much. And we need these new techniques. And this data is crucial because astronomers are handicapped in that they can analyze samples of data, but they can't follow up with experiments. They can only do experiments on virtual stars and virtual galaxies by crashing them together in the virtual world of their computer. So they're handicapped there. So data and data analysis is more crucial in astronomy than in most other fields. And let me mention a couple of examples. One example of big data is the distribution over the sky of the microwave background radiation, which has fluctuation in it in all scales. And although he didn't talk about it, Alex Allais has been an expert in showing how one can, by AI, take this large body of data and learn about the structure of the universe, the early universe, and dark matter, which exerts gravity and produces a lensing effect, distorting background objects, etc. So that's a big data sample and will be still larger when we have not just the marvelous data from space, from the Planck spacecraft of the whole sky, but we soon have some data on possible polarization in small areas of sky from a ground-based observatory called the Simons Observatory. So there's very excitement there in looking for patterns. And of course, one should be open-minded about very strange patterns. Things are disappointingly near Gaussian in many of these situations, but one should look for some very strange pattern which might exist and might tell us a great deal. So that's one example. And let me mention a second example of big data. This is the European Space Agency's Gaia satellite, which has surveyed our galaxy and offered data on the brightness, colour, and motions in 3 dimensions of almost 2 billion stars. This is of interest because our galaxy results from a merger of several subgalaxies of different ages and content. And the stellar orbits are partly phase mixed, but not completely. So if you can identify separate streams, as it were, which came from particular precursors, you can learn a great deal about the history of the galaxy just from this one sample. So that's another one. Let me now turn to a very different astronomical application of AI. This is the development of sophisticated autonomous robots which can operate beyond the Earth. The motivation for developing these is, of course, huge. The vast savings of scientific and practical, vast savings if we can get scientific and practical benefits from these without having to send people into space. At the moment, terrestrial robots are rather clumsy and limited in their capacities. And if we are to make full use of robots in space, and indeed on the ground, we need to not only make them mechanically more adept, but also allow them to sense different surfaces in a way that human skin can, etc. Indeed, here on Earth there's a long way to go before a robot can play football well or jump from tree to tree as well as a squirrel. So there's a long way to go in those techniques. Well, why do we want these robots in space? The most obvious challenge is for probing the surface of other bodies in our solar system. And already there are American and Chinese vehicles the size of a small car trundling across the surface of Mars, and some on the moon as well. They can navigate around rocks and other obstacles, and they can transmit data. But they can't yet decide what are the most interesting places to dig and obtain samples. But within 20 years, however, they will surely understand enough geology for scientific tasks. And of course, this can be achieved at a saving of hundreds of billions of dollars compared to the expense of sending humans and bringing them back with safety levels acceptable to the public for taxpayer-funded individuals. I should mention that the Artemis program, which is going to send people back to the moon, is going to cost nearly $100 billion. And going to Mars and making it safe could be up to 10 times that. And a robot, of course, can be sent cheaply. It needn't be brought back. And also, very important, the robots, the kind that are on Mars now, without very much more difficulty, they could be sent to the moons of Saturn and Jupiter, where there could be life. They're the most likely places, apart from the Earth, where there could be vestiges of simple life. So, robots can do many things. They can mine asteroids. They can assemble solar energy collectors in space, large structures, or on the moon without the need for humans. But we can't deny the romance of human footprints on the moon and Mars. But is it worth public resources? And perhaps, at the risk of self-advertising, I can mention that I co-wrote with Don Goldsmith a book called The End of Astronauts. And the main theme of this book was that beyond Earth orbit, we felt that the only human ventures should be paid for by private companies so that they can launch cut-price, high-risk voyages, taking the kind of individuals who are prepared to take those high risks. The problem being that the American public is very risk-averse, as we see from the fact that the 2 failures in 135 launches of the Space Shuttle were each traumatic for the American people and caused big delays. So we think it will be inconceivably expensive to send people funded by NASA to Mars. But on the other hand, it would be great if there are a few human beings on Mars by the end of a century, crazy adventurers. Elon Musk says he wants to die on Mars, but not on impact, and I think he's 52 now, so he might make it, and good luck to him. But it's a dangerous delusion to think that Mars is a destination from which we can escape the Earth's problems. Dealing with climate change is a doddle compared to terraforming Mars. Living on Mars is worse than living at the ocean bed or at the top of Everest. But there may be some people who just live there, and they'll be either in a cave or under some dome, and although it's too far from this topic, they may be important for the far future because they'll have every incentive to use cyborg and genetic techniques to redesign their progeny, and that may be the emergence of a post-human species while we live happily as humans here on Earth. Well, that's all I want to say about the importance of robots for exploring the solar system, and of course assembling large structures, that's going to be very important for practical issues like the asteroid mining, etc. I want to finish by mentioning a rather different topic, one in fundamental physics, understanding the ultra-early universe. Cosmologists have developed a consensus picture whereby we can extrapolate back our present universe to a very early high-dense state. We can extrapolate back with confidence to a time when the presently observable universe, about 15 billion light years across, was compressed to the size of our solar system. At that stage, the densities will be about nuclear densities. All the particles will have energies about the same as those that can be produced in a big accelerator like that at CERN. And from that time onwards, as the universe cools down, we have been able to corroborate this model by using the physics we understand to calculate what should happen, like the proportions of helium, hydrogen, and deuterium made in the Big Bang, and we get corroboration. But it's clear to everyone that many key features of the universe are imprinted at a far earlier stage than that. And as we extrapolate further back, then, of course, the physics is beyond anything that we understand and which we can reproduce here on Earth. And this is where we do need some new theories. And indeed, the most popular ideas involve the idea that the action which determined why the universe is expanding the way it is and what its content is, involve compressing the present observable universe down not merely to the size of our solar system, but to the size of an apple, even to microscopic size. A huge extrapolation, very far from any direct experimental verification. But there are theories, of course, which involve gravity and microphysical forces, which would, if correct, tell us what the conditions were like back then. One class of these theories, and just one class of them, is so-called superstring theory. And this involves the idea that a point in our three-dimensional space, if you magnify it enough, is a wrapped-up origami in 5 or 6 extra dimensions. So space on this tiny, tiny structure has an immensely complicated geometry. And the idea is that it is the basis of systems with that tiny geometry, which are the particles of our world and determine the forces. Well, the reason I mention that in the context of AI is that the geometry which is involved is extremely complicated, obviously, and moreover, the theorists know that there are literally billions of different types of folded origamis in 5 dimensions. And if we want to make progress, we've got to somehow sift through those and understand which might lead to a universe like ours when it cools down. And this is not something which probably any human mathematician could do, certainly not in a lifetime, but it seems to me a speculation, and it's been talked about by people who know far more than I do about it, that it could be that this task could be tackled, at least to some extent, by AI. And if it could, then it would be an interesting new kind of scientific discovery, because, of course, the hope would be that the machine explores a whole sample of these 5-dimensional origami, etc., and finds that some do have the properties of cooling down into a universe resembling ours. And if, for instance, a supercomputer churned away on this very elaborate geometrical problem and spewed out at the end the mass of the electron, or the standard model, or better still, predicted some new particles, then we would know that there was something in this theory, and that the computer had, as it were, made a great discovery. But it would be a discovery of a new kind. It would be a theoretical advance. But in most cases, when you get a result from analyzing a large data sample, and we've heard about this in drug development, superconductivity at high TC, and things like that, you can then go back and see why the winning entry was the way it was. And John Wheeler, the great theorist, famously said that if there's a huge advance in physics, then in retrospect it looks simple, and we think, why didn't we think of that before? Now, I think if anything comes out of applying AI to these very difficult mathematical problems involved in multidimensional spaces, which might be the key to the early universe, then I suspect we will never be able to understand them in that intuitive way. So we will have a kind of theory which we believe in because it works, but we never have the sort of insight into it, which I think we would say we do have into Einstein's theory and most other theories. And so I think that's something which is interesting for philosophers who do worry about the difference between competence and comprehension in other contexts for robots, etc. So I've gone on for long enough, but it's important that this could lead to a reduction in the depth to which humans can claim to understand their own theories, which would be disappointing in a way, although it would be wonderful if we did somehow get a unified theory. Well, I focused my remarks on astronomy and cosmology, but let me conclude with the sort of routine modesty which I think all physical scientists should put forward when they address interdisciplinary groups, which is to say that the greatest challenges are those faced by biologists. They're the ones who are studying the most complex aspects of nature on all scales, from cells to ecology. And they confront the bigger challenges, and they'll be held to even more and to greater human benefit by these marvelous and exciting new technologies. But in astronomy, things are very exciting because we have more data and the possibility of far deeper theories, all helped by developments in AI. Thank you very much.
Oh, you can do questions.
Okay.
So if the speakers could now come up, and we'll do the, by now, familiar panel discussion Q&A. Who would like to start? There we go.
I wanted to, the talks were all fantastic, but I would like to make a question on the last talk we had. If indeed string theory has these huge number of, but finite number of models, and if an AI finds it, say a good model that represents what we see, how is it different from basically finding a particular bit encoding that essentially runs our universe? I mean that, as you say, it's not about an insight here at this point. It's by finding the random seed upon which our universe exists. And so the question to you and probably to the rest, what would you call as insight? How would you say an AI has insight about what it's doing?
Well, as I say, I'm not at all an expert in string theory, but it's certainly assumed by some people that there could be many possible kinds of universe, different vacuum states with different microphysics in those. So our universe may not be the only possibility, although we do know, of course, that the laws of physics are the same in the entire part of the universe we can observe. But there are so-called multiverse theories, whereby our Big Bang is not the only one, and there could be other Big Bangs, separate space-times from ours, and in those, the physical laws, the laws of microphysics, could be different. And that's the kind of thing which one can imagine this theory might lead to. But let me just say that string theory is a marvelous mathematical construct, but there's no evidence for relating it to the low energy world, and there are other theories which are being developed by others.
Thanks. Who else has it?
Excuse me,
to
the
the
jocular
other-
answer would be 42.
Yes, right.
So I was a bit surprised that many of the panelists in this session mentioned the hallucination or the confabulation as a major issue in the context of the safety or whatnot. When from my understanding, what I see is that in fact, in particular in the context of the science, hallucination is absolute necessity, and that is actually the feature. After all, what we do is to come up with a scientific hypothesis, and then we try to verify or verify that that is not the case. So isn't the hallucination what we always do? That is to come up with a hypothesis that we don't know whether they are correct or true, and then verify them. So in a sense, it feels like it's not a bug, but it's more of a feature that needs to be in fact encouraged. And if I just take one more step, in fact, the hallucination that is made by the different models actually tell us that there's a variance in this kind of, let's say, model training. And then by suppressing the variance, I'm actually worried that that's going to increase the bias. So if we had to choose between the stochastic behavior and the deterministic behavior with a higher bias, I think the former is always preferred over the latter. Mm-hmm. What do the panelists think?
I'll say something about that. So first of all, I think that depends on what context of use you're talking about. So first of all, you're right that it is a feature, not a bug, of generative AI, because it's part of why we built these models in the first place is to generate novel outputs, right? The problem is the temptation and, frankly, the commercial kind of hype motivation to then sell that product for every possible use case, whether that kind of novelty is actually what you want for that application. There are certain kinds of applications where expected novelty that can then be explored is welcome. In other applications, which are either safety critical or trust critical, like scientific publication, like the publication of methodologies, data sets, scientific images, plots, right? Confabulation there is catastrophic, right? So it's understanding whether you have the right tool for the job. And frankly, a lot of people aren't getting training on what generative AI is good for versus other kinds of machine learning tools. And I've been shocked by how many researchers I've encountered who actually have picked up from the commercial hype that generative AI will be better for any research task that they have, which is a terrible misunderstanding of what the tools do. The other thing I'll just add is that the kinds of confabulations that you normally get from these tools involve reproducing variations of the most dominant pattern in the data. So actually what they aren't particularly good at is generating things that are truly novel, things that actually are really unexpected. And so if we rely too much on these tools to generate possibility, so people think about this in the context of story writing and script writing. Absolutely, a generative AI tool can give you new story ideas, but most of the time they'll be extremely cliched and familiar story ideas, right? And variations on what it already recognizes as common tropes. What you very rarely will see is a coherent but interesting story idea that you've never heard before. Mm-hmm. A human can produce that. So I would just sort of say, I don't think we should treat this as an inherent flaw of the technology. It's not. It's a flaw in how we understand its uses.
Good. Okay. Does any other member of the panel want to comment on that?
You might otherwise look into this small but growing literature on open-ended AI, which is explicitly about how do you drive continuous exponential growth. And yes, you now have to be doing out of sample, not in sample for the hallucinations. Otherwise, you will get the convergence. So how do you do simulated annealing logically? So there is a possibility of creativity and such happening, but probably not in this period.
Who else has a question, or who has the microphone?
I'll make a comment on this. I think creativity in science is often well informed, and that ends up being more productive, right? So we have a history of some AI systems in science that generate a hypothesis, and the reaction is, that sounds good, but is that going to be promising? What's the rationale for hypothesizing that? Is it worth pursuing that versus other hypotheses that a human scientist would come up with in an informed, rational and creative way? So I think that the hallucinations are not necessarily a way to be creative or think out of the box as you may be thinking about.
John?
So one of my surprises after AlphaFold was released, and I had many pleasant surprises about how responsibly people use it, but I did see we have seen two patterns in both directions of kind of unjustified either pessimism or hype. In a very technical sense, and I apologize, this will be slightly technical, like one statement is on in a creativity vein, confident assertions that AlphaFold can't do proteins with a novel fold that have not been observed before. And I still see this, and I keep thinking, did you not see the figure in the paper that clearly demonstrated this and all the papers that do it? And so we see unjustified pessimism or assumption because of how they see the connectivity of the algorithm, what it must do, which is not a good way to assess AI systems. We also see unjustified optimism of, we know and we've well characterized that AlphaFold has very limited capabilities with respect to single element changes in a protein, which surprises everyone, including ourselves, that something can be this accurate and not sensitive to that. And we know all these things through careful benchmarking. We take these questions, we make reasonable sets to test them, we check. And people do this in LLMs, of course, and I work at a place that builds LLMs, but how do we get the public, or how can we help them develop skepticism? And I did find myself maybe having, disagreements with some of the assertions made even in this talk on what might be doable or not doable, but I'm also thinking, well, what about this test and this test? And I feel like I can argue and come to evidence. Can we create an empirical mindset in scientists in the community such that instead of asserting one way or another what these machines can't or can't do based on our assumptions, that we actually get the community to look and check and do the little experiments? Is there a way we can shift this practice?
I think that's a great comment. We worry about misinformation and the amplified misinformation caused by AI. I think that science is, in particular, it has been a place where a lot of misinformation is spread around, whether it is by in social media by people that want to paint a different picture, or whether it is by oversimplifying a scientific finding, or whether it is, there's millions of ways in which science is portrayed in ways that are not very accurate. And I think that you're pointing out to some of those cases for your work. I think there's an aspect of a scientific responsibility and being very, very accurate on what we say about other work. And sometimes, we talk about other work to fit a narrative of a point that we want to make, and we exaggerate, or we make a comment that may not be exact, but it tells a story in science, and that's helpful. So it is part of the practice of science. But I think there's also the onion of how science gets disseminated and potentially used, where there's a lot of opportunity in those processes for misinformation. It's a very hard problem, I think.
If I could just add something to that, I think it's a good idea to look at other problems that we have with public understanding of the power and limitations of science, for example, misinformation around vaccines and things like that, and what drives that, and what doesn't fix it. And unfortunately, we found in a lot of cases that, you know, kind of simplistic approaches to public AI literacy or public digital literacy or scientific literacy fail because it's often conceived as if it's a knowledge lack. And the problem is often much more complicated, that it's driven by narratives and values that people associate with science. And one of my worries about AI, and I've seen the same thing you're talking about, you know, as much as I spend a lot of time telling people what these tools actually can't do that they think they can, I also end up having to correct errors on the other side, where they say, well, it will never do that. And I say, no, actually, probably will or already does. But I can't fix that problem often just by correcting that information, because what I find is there's often a narrative that has already been woven in their mind about what these tools are for and who they benefit. And the same thing happens with vaccine misinformation, where the story always comes down to they've framed this in some way by thinking about science as corrupted by commercial motivations or political motivations. And we unfortunately already have AI wrapped up very obviously with commercial motivations and increasingly with governments who want to use it for surveillance and various other purposes. So I am not terribly optimistic, actually, because I don't know how you fight that. If we can't fix it for vaccines, I don't know how we fix it for AI.
I think even within the scientific community, though, I think we need more mini-science. Like, you know, I'm not the first to say this, but I do like the assertion that, you know, the best science show on television was probably Mythbusters, right? Because it's simply, they had a question, and they designed, often very imperfect, but they did an experiment, they got an outcome, and they talked about that outcome. And I feel like a lot of the people that talk about AI don't follow up with the mini experiments, including scientists, like this assertion you can or can't do something.
John, I'll add my, I guess it's a micro experiment that I did for a skeptical colleague. We fed his publication list into ChatGPT-4, and the prompt was, given the things that this person has worked on, what were some missed opportunities? You know, at what year in his publication list were there missed opportunities where, based on what he was already doing, he could have done something else? And it spit out 5 or 6 things, and he looked at it, and about 3 of them he said, oh yeah, I thought of doing that, but I couldn't get the funding for it. You know, so it actually is pretty good at things that a lot of people would say, no, it couldn't possibly do that. You know, it's just probabilistically adding words to the end of something.
Can I add something here, which is something we haven't talked about yet, that we need to practice interdisciplinarity, because when we're thinking about now understanding the operations of these systems, we simply won't do by limiting it to sort of technical understanding. These are socio-technical systems at the end of the day. And I think that up until this, you know, past couple of years, the conversation has been dominated by kind of scientism, right? Where there has been a prioritization of certain forms of knowledge in the way we explain, understand, talk about results, talk about the functioning of the systems. But we're increasingly seeing biologists, anthropologists, psychologists, many other disciplines really contributing to describing limitations of these systems, describing how we can sort of understand capacity and potential in these systems. And I don't think that we'll sort of step forward into having like well-informed engagement of these questions if we don't practice kind of even-handed inclusive conversation across disciplines. because we're simply moving into an era now where these systems are standing in for cognitive functions. But human cognition and how we understand the world isn't just the mechanism of prediction or the various other things that these systems are doing, formal linguistic capacity. It involves a distributed knowledge that builds over time, and we simply need to be inclusive about who's contributing to the conversation.
Okay, I'm going to have to move us on to our last breakout session. So if the magic that controls the slides could put up our assignments, how do we do that? Yes. Okay. Well, with the challenge of previous session chairs. Hello. Wow, you must be talking about interesting things. Not this table. This table is silent. Okay, with the challenge by previous chairs, I've decided we'll call on tables in the order of the digits of pi, omitting duplication. And is Terry still here? Terry can tell us what's known about the randomness of the digits of pi. Okay, so table 3 goes first.
So we have the summary statement that our table came to no solutions, but had a good conversation. We focused on 4 different topics, I think, or maybe 3. The question of narratives, and so we were really kind of triggered by the conversation before about whose narrative is right, and is the narrative accurate enough, or are there mistakes in the narrative? And so some of the topics that pinged off of that is whose narrative is the narrative, or whose narratives are important to control. How would you interrogate the failure and success modes of a non-human intelligence, and therefore come to some kind of narrative, if that's even a useful structure for understanding it, which is probably the way the public will come to understand it someday. And then we kept coming back to the lack of reproducibility from this morning, that and how that challenges all of the pieces of that story. Whether if you ask a chatbot one question now, and then in a week or 3 months, it's a totally different answer because changes have been made. How do you even interrogate that kind of a system? We had a brief discussion about how feedbacks of, if you took one chatbot into another chatbot, it spins off, and Bill said he got them to spin off and say that it would destroy humanity in the partner-to-partner conversation. But we expect that one day the internet will be filled with chatbot output, and so the feedbacks will start to come. And so that's an important part of the stability or instability. And so what kind of filters are needed, or guardrails that could be resilient to that kind of complex system, which you might not even know what the flow chart looks like. And then the last piece, which we laughed about maybe more, was what's an authority that is appropriate to decide what is right, wrong, the other. I mean, we're sitting in the Royal Society. That's one conjecture. There's this great opportunity for AI to democratize science, and maybe people from outside of the traditional locations might have good ideas that are going to be facilitated by this. But then if peer review is totally overrun, if journals are overrun, what do you do with that complex of ideas, and where some involve misinformation or disinformation? And so Bill had a nice concluding sentence, was science advances by a series of wrong papers. So maybe we're just continuing that way all the way along. So that's us, 3.1.
Okay, 3.1.
Okay, so we talked about a lot of different things. I think one of the main threads was on the use of social media in the peer review process. So there was a discussion about the impact of social media, the fact that it's a tool for unknown authors can gain traction on Twitter, but reputation still, of course, plays a role. there is this sense that on Twitter, people are kind of more critical on internal media rather than Twitter, although I haven't found that. So there's this discussion about, the use of internal forums like Discord to kind of be honest about papers. There was also discussion about so then we went into a discussion about the use of large language models in science. So it was noted that arXiv published a report, I think a few months ago, on kind of noting that certain words kind of jumped in frequency in 2023, kind of, telling us that the use of language models in scientific writing has certainly, it has a measurable impact. And it was also noted that arXiv they're even aware of this at the individual author level, because they can look through your history of arXiv submissions, which is, and then there was a discussion of kind of the ethics of that, and then there was a discussion about the potential for systems to generate publishable scientific work completely automated, so just using LLMs for papers, and whether that has useful applications like kind of filling in holes in the literature, and then there was a discussion about the ethics of that, the ethics of kind of submitting AI-generated work, even as an experiment, to a journal. And yeah, so at a meta level, this summary was also generated by AI. So.
Okay, 3.14.
Yes, we had basically one provocative statement starting with why does AI lead to so much misinformation? There's something special about the word. Basically, that's how we started. So, and from there it went downwards. Okay, so basically the first thing mentioned was that the word AI was not the first choice or the only choice when the term was coined. There was another term, technology, and there was one group of people who preferred the technology view, but there was another group of people that in the early days thought AI sounds philosophically more interesting, and so we are stuck with a word that has all these extra hallucinations associated with it. One comment here was that AI, a term that AI is often or used to be used for every type of algorithm where it's not really clear what algorithm you use. Once you know which algorithm you use, you call it A star or breadth first search or whatever, and then it ceases to be AI. Then one comment that I wanted to mention is going backwards, it looks like things that we thought were difficult turned out to be easy, things that we thought to be easy turned out to be difficult. Very classic, actually, mistake in science often. As somebody said, progress in the future is always far away. Looking back, it actually was a very rapid process. Then we move to a more serious topic, anxiety. AI creates anxiety amongst a new, especially also young people, not just the middle class. Loss of perspective, loss of opportunities. Will it displace people? Basically, one example was brought. Photographs actually displaced painting more or less. I mean, not entirely, but to a large extent. You don't have to be very competent to make good photographs. If you're just press a button, pick a good picture, and you're done. That is something that's very new. The problem with AI for example, for helping creativity, I mean, one argument is it helps creativity. More people have now access to creativity, but the disadvantage is a mirror of past humanity. That was the word that was suggested. So the creativity is limited. Humans basically create creativity with using past techniques. As a positive aspect, let's not end in the Valley of Tears. As a positive idea is it might actually introduce a new style of collaboration in the future, a new way of dealing with difficulties and not worrying about too many vagaries of boring routine work. And with this, I'm concluding.
Good. 3, 1, 4. We skip 1, 5.
Okay, so we actually started, I think, with this automated hypothesis verification. I think that's from the first speaker, Yolanda's talk. So, right, so we discussed, like, whether this automated hypothesis verification would be the feasible way to verify the scientific findings reported in literature or reported in scientific papers. And I think the discussion around the table is if the hypothesis can be transformed into some kind of a code or some kind of like a SQL queries, which can be executed, then it might be like, sensible to do the verification in that way, I mean, automatically. But then I think it was also mentioned, the initiative, I think, by Terence Tao. So the initiative actually, like, to break down the kind of a mathematical proof into some computer verifiable problems, and then through crowdsourcing, right? And then basically, like, there's multiple pieces can actually be gathered and then to do the proof. So in a way that it's doing this human in the loop kind of automated hypothesis verification, so that's related. So I think that's interesting. But then I think it's also noted that, I mean, this kind of automated hypothesis verification is domain and data and also task specific. And it was also like said that sometimes it might not be that crucial to perform this kind of automated verification, because it's actually like all related to kind of a human understanding and communication, right? So a human actually communicate with another human, especially like, if the humans work in the same domain, then the scientific discourse would rely on the mutual understanding and also rely on the, other humans appreciate or understand the kind of argument, the reasoning trains behind the argumentation process. Right, so I think we started from this, then we move on to do this, like, whether AI can actually help with the hypothesis generation. So again, I think we say that, like, specifically in some area, like, I think there's also like a talk yesterday relating to molecular applications. So it might be possible to actually using AI to generate hypotheses, but then it's still like rely on humans. So it's important to have the human to actually do the synthesis and also testing. And I think the other thing we discussed is AI might be quite good to actually predict the research trends, right? So I think it was like mentioned that some researchers in University of Chicago, they actually work on predicting emerging hot fields using AI. But then we also say, we also discuss something like, maybe we can leverage AI to do the scanning and also synthesizing information from vast, scientific literature from experimental fields such as material science. But again, I think because in that field there's a lot of data reported in table and figures, so it would be good if AI can actually synthesize information from those multi-model data. But then in this process, we still require human to do this enhancement. And then lastly, I think we briefly touch this unjustified skepticism, right? So, but then it was also discussed, sometimes this kind of skepticism might just be resolved over time. I think that's everything in our table. Yeah, thank you.
Thank you. And since there's no table 9, it goes to table 2.
Okay, I'll keep this relatively short. First, we talked about incentives. So there's a lot of conversation about incentives being the issue when it comes to some of the problems with AI-generated content. And then there was a bit of a conversation about where the responsibility lies for changing those incentives. Some of the actors are potentially the funders, who require a certain number of publications or type of publications. Another actor is the institutions, like universities themselves, who do the hiring, and that they should take more due diligence over who they hire and what their expectations are for academics in their institution. There was a bit of conversation about the amount of requirements that are already being put on academics around data protection and DEI, and whether responsible AI statements would be another burden potentially upon them. Then there's a bit of conversation about the sort of explosion in publications that some conferences are seeing, and one example given was the NeurIPS conference received apparently 22,000 abstracts this year compared to 12,000 last year. And how do you actually filter those, and how do you limit some of the top authors from submitting more than a single paper? What else was there? There's a little bit of conversation around AI for peer review and whether that would be a good thing or a bad thing, and improve the quality, or actually, just inject more useless reviews into the system. A bit like Table 3, we talked about, or I threw in the word enshittification of the internet, which is this idea that you get a lot of crap that filters through the internet through AI-generated content, and whether this would also happen within the academic sector. And the final bit, so I have a policy background rather than a science background, so but working here, you do kind of get used to some of the science conversations, but then we started talking about AI for string theory, and I just totally went over my head a little bit towards the end. But I think it was a conversation about how we could measure the outcome of something that is so opaque. And I got lost a little bit after that, but it sounded like it was an interesting conversation about string theory. And that was us.
Okay, thanks. Okay, and let's thank all the rapporteurs for their... And before I turn things over to Alison for the forum closing remarks, I want to say on behalf of all of the U.S. speakers and invitees who crossed the Atlantic to come here, to thank the Royal Society for its wonderful hospitality and for these beautiful surroundings in which we could hold this meeting. So thanks.
Well, thank you. And part of my closing is to also thank everyone, particularly from the US, for coming all this way. It's been a fantastic meeting. I hope you will agree with me. And this is partly through the real thought and efforts gone into from the speakers to really incredibly high quality talk. So thank you very much. But also everyone for contributing as well. I hope you enjoyed the format of having presentations and then having times to exchange ideas and really get this sort of snapshot of where we are at the moment in AI. It's not just about the algorithms, as we know. It's about the context of use across the whole of science. But the last session, for example, really making us thinking we also need to reach out to think about some of the social sciences aspects of what we do, and hopefully going forward we will be factoring that in as well. So I was asked to do the closing remarks. I say it's basically an opportunity as well to thank everyone, particularly thanks to the organising team. I'm looking over in that direction towards Anna, and the other direction towards Ash. So that they've worked incredibly hard for a good number of months, getting particularly the organising committee together as well on Zoom to be able to come up with this meeting. Also, thanks to the local organising behind the wall as well as out the front, who've meant that our 2 days have gone very smoothly. I'd like to particularly thank the organising committee and those that are still here. If they would like to come up to the stadium, there is a small gift of thanks. So if they would like to come up. Fabio. too as well. Of course you do as well. There we go. And one more to Bill.
Is it a GPU?
I think they wish. Just as a final point, there will be a short write-up of this meeting that will be produced, and it will be circulated to all participants in due course. Don't worry, the participants will be listed, but no remarks will be attributed to you. If you would not like to be listed, please could you contact Ash or Anna, but hopefully you will be looking forward to that email coming through to you as a reminder of some of the key points for the meeting. So with that, I will formally close the forum, and thank you all again for all your participation.